In this video, I'll show you how MATLAB can solve the Laplace equation using an iterative method. Here, we'll use the Jacobi method. We solve again the two-dimensional Laplace equation given by del squared phi equals 0. We discretize the Laplace equation in the usual way, but here we write down an iterative scheme. We put the ij term on the left-hand side and pull all the other terms to the right-hand side. We then label the iteration steps by n plus 1 on the left and by n on the right. This is the Jacobi method. We'll apply the same boundary conditions as in the direct method solution. 0 on the bottom and the sides, and 4x times 1 minus x on the top. Let's briefly discuss the main algorithm in our MATLAB code. The computational engine of the code is the Jacobi iteration. We iterate the solution on the interior grid points and fix the solution on the boundary grid points. We wrap the iteration in a while loop and run the loop as long as the estimated error in our solution is greater than some specified error tolerance. OK, let's write a MATLAB code. We start the code by defining the rectangle and the grid parameters, exactly the same as we did in the direct method. So I can cut the code from that program and just put it right here. Very nice when you can do that. The next step is to define the iteration parameters and the initial condition for phi. So I define an epsilon EPS variable to be 10 to the minus 6. That's going to set the convergence criteria for our iteration, for our Jacobi iteration. I want to iterate all of the value of phi at all of the internal grid points at the same time. So to make that simple, I define indices, index x to be 2 to nx minus 1, just the internal grid points. The boundaries correspond to 1 and nx, so I exclude that. And index y from 2 to ny minus 1. I'll use that to index phi in the iteration. Then I set phi equal to 0 everywhere on the grid. The starting value for phi on the internal grid points will be 0, and then the value of phi on the boundaries will need to be adjusted. Next, we define the boundary conditions. Phi is 0 everywhere, but here I specify it again so that one can easily change boundary conditions. So phi for all x values at the first y value corresponds to the bottom of the rectangle. That will be 0. Phi for the first x value and all y value corresponds to the left of side of the rectangle. That's 0. And phi for the largest x value and all y values corresponds to the right side of the rectangle, and that's also 0. So the top of the rectangle is phi for all x values for the largest y value, and that's set to 4x times 1 minus x. So all the boundary conditions are set, and the next step then is to code the Jacobi iteration. Here we code the Jacobi iteration. We have two values of phi on the grid. What I call phi is our current iteration value, and phi old is the previous iteration value. So we're going to be comparing phi and phi old to determine whether phi has converged to our convergence criteria. We set error here equal to twice our convergence criteria, 2 times epsilon in the beginning, and then we'll be calculating error as the iteration evolves. I want to count how many iterations we're doing, so I have a counting variable. I call that nCount and initialize it to 0. So our iteration then is going to be a while loop. So while error is greater than epsilon, EPS. So EPS is this 10 to the minus 6, and error we're going to have to calculate after each iteration. So let's see how we do that. So I increment nCount by 1, keeping track of how many times we go through the iteration loop. This here is then the main computational engine of the code. That's the Jacobi iteration. So I do it for all of the internal values of phi at one time, doing the entire matrix in one line of code. I have this index sub x and index sub y, so all of the internal grid points of phi is equal to 1/4 times phi of index sub x plus 1, comma index sub y, plus phi of index sub x minus 1, comma index sub y, plus phi of index sub x, comma index sub y plus 1, plus phi of index sub x, comma index sub y minus 1. And that should be exactly the Jacobi iteration. So we've done the Jacobi iteration one time, and then we compute the error by looking at the difference between phi now after one iteration and phi at the previous iteration. So I turn phi into a vector here and phi old into a vector. That's in order to make these this maximum function in MATLAB return a single value. So I'm taking the absolute value at each value of phi at each grid point, taking the absolute value of it, and then taking the maximum over all of the grid points. So maximum will return a single number, and that will go into error. And they were trying to get that difference then between two iterations to go down less than epsilon, what we set to 10 to the minus 6. Okay, this bit of code is an extra. I just show you the code. It's not actually needed here or even used, but it's a test to see if your iteration has diverged. So if any value of phi is not a number, or any value of phi is infinity, then I will print out iterations diverge and then return. So that's useful when you're first writing the code in case you have a bug in the code, and it's useful for other types of iteration, other types of equations that you might develop iteration schemes that actually have the potential for diverging. Okay, and then at the very end we set phi old equal to phi before we run the next iteration. This fprintf statement here I like to run when I'm writing the code, debugging the code. It keeps track, it prints out the error after each iteration, so you can make sure that the error is decreasing with each iteration. And you can watch then the progress of convergence to your solution. It will slow down the code a lot. When you print something all the time on the screen in MATLAB, it makes the code run slower. So usually you comment it out at the end. Then when we get to out of this while loop, it means that we've converged. I like to print out then how many iterations it took to converge, just so you can see how your code is running. Finally, we want to graph the solution. We can just cut and paste the graphics part of the code from the direct method. You don't have to change a thing. So it's very nice when you write code so that you can reuse your code in other codes. So you do a graphics or you do some initialization routine, and if you can reuse that when you write your next code, you're saving yourself a lot of time. So you try to write things in a general way. Let's run the code. I have the editor now docked in the full MATLAB. So we hit run, and then we get our solution. So the same graph that we got for the direct method. You see it took 10,311 iterations to converge. We have all the variables here available to us. We see that the error is less than 10 to the minus 6, which is why the code stopped and after 10,311 iterations. If you like, you can look at the values of phi itself. It's a 101 by 101 matrix. Everything's accessible. So when you actually write this code, you're writing it in the MATLAB environment. You're looking at the variables. You're putting breakpoints here. And for instance, if we put a breakpoint here, we can run the code, and then the code will stop at the breakpoint. So you're using all of the tools of MATLAB while you write this code to debug it. Iterative methods for solving PDEs are easy to understand in code. We have used the Jacobi method, which may not be the fastest method to use, but it doesn't really matter. Our code runs fast enough. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.